Section 1.5, divisibility. We start with the following definition. If A and B are integers, and if A is not equal to 0, we say that A divides B if there is an integer C such that B is equal to AC. If A divides B, we also say that A is a divisor or a factor of B. Notation. Vertical line means D divides N, or which is same, N is divisible by D. For example, 4 divides 12 because 12 is equal to 4 times an integer, which is 3. 4 does not divide 15 because 15 is 4 times a non-integer number. Theorem 1. Let A, B, and C be integers, and A, B are not equal to 0. If A divides B and B divides C, then A divides C. It's exactly what is written here. How we prove it? A divides B. Once again, it's given. A divides B. A divides B means B is A times an integer. Similarly, B divides C means C is B times an integer. And now let us start from this. It's over here. And replace B by AE. If we replace B by AE, we get this. Lastly, let us shift parentheses to the right. AE times F is equal to A times EF. Since both E and F are integers, EF is an integer number. So C is equal to A times integer, which by definition of divisibility means A divides C. Example, 7 divides 56, 56 divides 168, therefore 7 divides 168. Theorem 2. Let A, B, C, M, and N be integers. And suppose C is not equal to 0. If C divides both A and B, then C divides any their integer linear combination. By linear combination of A and B, we mean this expression: A times M plus B times M. We call this a linear combination of A and B. So, no matter what is M and N, if M and N are integers, C divides this. In particular, if M is equal to 1 and N is equal to 1, C divides A plus B. So, if C divides A and C divides B, C divides their sum. Or, if we put M is equal to 1 and N is equal to -1, this becomes A minus B, Conclusion: if C divides A and C divides B, C divides A minus B. So these are two particular cases of this general theorem. How do we prove it? Once again, we start from this and this. C divides A means A is equal to C times K1. C divides B means B is equal to C times K2, where K1 and K2 are some integer numbers. Now, we start from MA plus MB. We replace A by this, done. We replace B by this, done. Lastly, factor out C, done. Note that since M, N, K1, and K2 are integer numbers, this is an integer. Conclusion: MA plus MB is C times an integer. Therefore, by definition of divisibility, C divides MA plus MB. In particular, 11 divides 22, 11 divides 33, therefore 11 divides 319 because 319 is an integer, a linear combination of 22 and 33. Folks, any questions here?
I have a question.
Yeah.
In the homework and on the test, so like you're explaining like through your proof, telling us, well, we see that MK, N, and K2 are all integers, so we know that that's an integer, but it's not written in your proof. So on the homework and on the test, do you expect us to write those out, or is like if we write it like how you write it, that's going to be fine?
Excellent question. If you do this, it's absolutely enough.
Okay, thank you.
So once again, during a lecture, I provide even more details than it's written here. But on tests, you do not have to be as detailed as I am right now. Next, here's an example. Show that 8 divides n squared minus 1 if n is 4k plus 1, where k is an integer. How do we do that? We start with n squared minus 1. Step 1, replace n by 4k plus 1. Done. By algebra, a plus b squared is a squared plus 2ab plus b squared. Cancel out 1, done. Factor out 8. Note that since k is an integer, 2k squared plus k is an integer. So n squared minus 1 is 8 times an integer. Therefore, 8 divides n squared minus 1 by definition of divisibility. Similarly, in order to show that a minus b divides a squared minus b squared, where a and b are integers and a minus b is not equal to 0, we just observe that by algebra a squared minus b squared is a minus b times a plus b. So a squared minus b squared is a minus b times an integer. Therefore, a squared minus b squared is divisible by a minus b. I encourage you to take a look at all examples from Appendix 1. There are lots of important examples.